Okay, so I'm going to bring up now an important special case. So let's say that the only force acting on you is gravity, and we're not standing at the surface of the earth, which we'll get to in a second. Then what is your acceleration? So what is A equal to? Well, we can do a net force equation. So mass times acceleration is equal to the sum of the forces. In this case, it's just the gravitational force with it, which is G mm over r squared. We'll use capital M for the mass of whatever object is pulling. Okay. Well, given this mass and that mass are the same, and we can divide them out, which means that the acceleration you experience from gravity is equal to Gm over r squared. Okay. G is constant. If you know the mass of something and how far away you are from it, then you can find your acceleration of gravity. Okay, now at the surface of the Earth, the mass of the Earth doesn't change regardless of how far you are away from the Earth. This is relatively constant too. And so we say that all three of these things are constant for anyone near the surface of the Earth, and that's where we get 9.8 for gravitational acceleration. Now this number is not exactly 9.8, and it varies quite a bit. So we use G. We say it's 9.8. Okay, let me clarify. The acceleration that you should experience from gravity is based on these things. What you actually experience is slightly different based on where you are on Earth and where the how far you are away from Earth's surface. Maybe there's like in a certain area of the Earth it's a little bit more dense, and so being close to there you have a stronger gravitational pull, and so stronger gravitational acceleration. And so the value of acceleration from gravity changes, but G is going to be kind of different because what we experience and what we predict are different. In addition, because the Earth is spinning, there's a small effect from that too. We've talked about that effect before. It's very, very tiny, but it does exist. Okay? And so there's a lot of variation in acceleration from gravity depending where you are on Earth. And so you're at the top of a mountain or something. And you can see a table on page 335 in your book that shows the value for acceleration of gravity at some different places on Earth. Okay, so but in general, if you want to know the acceleration from gravity on something, you set up a net force equation and you can just divide out m to get A. So now that we've done this, if Earth's radius is equal to 6.37 times 10 to the 6th meters, and Earth's mass, so Earth's mass is 5.98 times 10 to the 24th kilogram. Plug these values in and go ahead and find what acceleration from gravity is. Okay, and so I got about 9.8. I guess you could go to 30 if you want to. I mean, there's a lot of place values here, and technically, given the precision, well, we don't have a lot of precision on the radius there, so probably we could stop at just 9.83. Okay, and this would be meters per second squared. Okay, and we use 9.81, and we were mentioning some of the reasons for this a minute ago, depending on where you are on Earth and the effects of the rotation and the effects of the fact that Earth is not perfectly spherical. That's why we use this, but they're very close. Okay, so we can also use this to find out maybe how fast, if something has a circular orbit, like how fast it's orbiting. Okay, because if the only force acting on something is gravity, Okay, so that ma equals g mm over r squared, and that a is equal to just gm over r squared. Well, for something that has a circular motion, so something rotating, that a is going to be equal to v squared over r. Okay, so that v squared over r is equal to capital G, capital M over r squared. Okay, so what that means is that the velocity for an object with a circular orbit is going to be equal to the square root of G times M over r. Okay. Another interesting conversation comes up with acceleration from gravity, has to do with the difference in acceleration between, like, if you're standing on Earth, because you have height, okay, then the distance from the Earth center between your feet and your head is different, which means that you have a different acceleration from gravity between your feet and between your head. Now, if you wanted to calculate that difference, it'd be very difficult because you would basically be subtracting gm over r squared minus gm over r plus h squared. Okay, yeah, this is going to just be really tricky because h is super, super, super small. Okay, but hopefully you're starting to notice something. Maybe you've seen something like this in calculus. And so what you can do, if you're looking for small variations in r, you can take the derivative of this with respect to r. Okay, so dA dr is going to be equal to negative 2 times g m over r cubed. Okay, and so dA, or the change in acceleration, is equal to negative 2 gm over r cubed dr. So let's say that somebody has a height of 1.7 meters, then we would use this for dr. And then the mass of the Earth is 5.98 times 10 to the 24th kilograms. The radius of the Earth at the Earth's surface is about 6.37 times 10 to the 6th meters. Okay, and so the question I have is, what difference in acceleration does this person experience between their feet and their head? Okay, so go ahead and do that calculation real quick. Punch in those values. And so I get a change of about negative 5.25 times 10 to the negative 6 meters per second squared. And so what that means is they experience this much less gravitational acceleration, or a person standing on Earth experiences this much less acceleration from gravity at their head than they do at their feet. All right? So let's say now, though, that instead of standing on Earth's surface, you're orbiting that same distance outside of a black hole. Okay? And this black hole, instead of having the mass of the Earth, let's say that the black hole's mass was equal to 1.99 times 10 to the 31st kilograms. Okay, given this, I want to know what acceleration from gravity would be in that case. Let's use the same value for r, okay, and the same value for dr, and find what dA is going to be equal to. So not the acceleration, but the difference. Okay, so go ahead and find dA, given you're floating outside of this black hole, or being sucked into it. Okay, so what I found is that you have a difference of about 17.5 meters per second squared of acceleration between your feet and your head as you're getting pulled into the black hole. Okay, so this is not, this means that your feet are being pulled faster than your head. Okay, and so the process of getting pulled into a black hole is called spaghettification, and the reason why is because this is what happens. Okay, 17.5 is almost 2 times acceleration from gravity of difference. Okay, which means that there's quite a bit of difference in the amount of pull on your feet versus the amount of pull on your head as you're approaching this black hole. And so you literally just get like stretched until you don't exist anymore, is what would happen if you were to fall into a black hole. Okay, you'd just stretch and stretch and stretch until you'd be gone. All right.